In this video, we will explore solving nonlinear inequalities. Specifically, we will focus in on solving inequalities involving polynomials or rational expressions that are of the form given here, where we want to know when something's entirely positive or entirely negative. So in this case, we have a rational expression, which we call as a polynomial over a polynomial, and we would like to know where it is bigger than or equal to 0. Now, to aid us with this motivating example, so this example is going to help us generate the general procedure, I've sketched the graph of the function to the right. Because of the x minus 1 term in the denominator, our graph will have a vertical asymptote, being the line x equals 1, and 3x plus 2 in the numerator tells us that the graph crosses the x-axis at minus 2/3. And if we would like to know where it's entirely positive or entirely negative, one way to think about this problem would be, where does the function change sign? That is, where does the function go from, say, positive to negative, or negative to positive? And note, at least empirically, looking at the graph that we've drawn, it changes sign at minus 2/3, which corresponds to where the numerator is 0, and it changes sign at x equals 1, which corresponds to where the bottom is equal to 0. And in general, this is exactly how it will work. So what we need to do is find what we would call split points. And the split points are going to correspond to the numerator being 0, or the values that make the denominator equal to 0. So 3x plus 2 equals 0. That implies x is equal to subtract 2, divide by 3. Or where the denominator is 0. X minus 1 equals 0. That implies x equals 1. And the reason that we are calling these split points is we are thinking of them as splitting up the real axes. So minus 2/3 and 1. And what this is going to do for us is give us 3 what we will call test intervals. You have minus infinity up to minus 2/3, minus 2/3 to 1, and 1 to infinity. And on each of these 3 intervals, our function will be entirely positive or entirely negative. So to determine which of these it is going to be, we have to pick test points. So we pick maybe the easiest possible point we can in each one of these intervals. So for example, you might pick in this first interval 0, in the farthest interval 2, in the left interval maybe minus 1. And the value of our expression at each of these points will tell us whether our function is entirely positive or entirely negative in any one of these intervals. So let's see, if we're at x equals minus 1, we'll have 3 times minus 1 plus 2. Let me make that a minus 1. So once again, we'll have 3 times minus 1 plus 2. Divide it by minus 1 minus 1. So looking at our expression, we will have a negative in the top, divide it by a negative in the bottom. And a negative over a negative gives us a positive. And it turns out we don't necessarily care what the number is, we just care that it's positive. And that means everywhere in this interval, the expression will be positive. Then we go to our next test point, x equals 0. So when we plug 0 into our expression, 3 times 0 plus 2 over 0 minus 1, we end up with a positive in the top, a negative in the bottom. So a positive over a negative gives us a negative. So from minus 2/3 to 1, our expression is negative. Then at the test point in our last interval, x equals 2, we'll have 3 times 2 plus 2 over 2 minus 1. So a positive divided by a positive gives us a positive. Our expression is entirely positive from 1 to infinity. And once we've indicated via these pluses and minuses where the expression will be positive or negative, we can go back to the original question and we can summarize our solution. We would like to know where it is bigger than or equal to 0. Well, it will be positive from minus infinity to minus 2/3, and it is equal to 0 at minus 2/3, so we include that. And then we also need, so we're going to union this. This will be 1 up to positive infinity. And in terms of sketching a solution set, we can shade in on the number line that we have above. And we make sure that we draw solid circles at minus 2/3 and 1 because they are included in our solution set. And this really nice procedure can be outlined as follows. So if we would like to solve and determine where a polynomial or rational expression is entirely positive or entirely negative, we use the exact procedure we've discovered on the previous slide. We find these split points. That is where the numerator or the denominator will be 0. We take these numbers we come up with as split points and we arrange them in increasing order, so from smallest to largest, and we break up the number line using them. Then in each one of these intervals that they determine, a test interval, what we are going to do is pick a test point. And if the value of the expression is positive at a test point, the expression will be positive at every point in the test interval. And similarly, if the value of the expression is negative at a test point, the expression will be negative at every point in the test interval. And then that allows us to take that information and answer the desired question. So let's put this to work. So in this example, we would like to know where this polynomial expression is bigger than or equal to 0. So the first step we have in terms of solving this would be to find those special points that we called split points. So what we would really like to know is this polynomial expression on the left, 2x minus 3 times x minus 1 squared. Where is that equal to 0? Well, this equals 0 would be 2x minus 3 being 0, or x minus 1 equals 0. So x equals positive 3/2, or x equals 1. So we take our split points and we arrange them in increasing order and we label the number line with them. So 1 and 3/2. And this takes the number line, and in our case it breaks it up into 3 possible intervals where our polynomial expression can be bigger than or equal to 0 or less than or equal to 0. And what we need to do is pick a test point in each of these. So we pick the simplest possible number we can. So in the leftmost interval you might pick something like 0. In the middle interval, 5/4 is right in between 1 and 3/2. And then bigger than 3/2 would be, say, the number 2. And what we need to do is determine the value of the expression at each one of these test points. So if we start with x equals 0, if we plug that into our expression, we have 2 times 0 minus 3 multiplied by 0 minus 1 squared. And we need to know, is this number positive or negative? And recall, we don't necessarily care what the number is, just the sign of it. So the first part is negative. Something squared is always positive. A positive multiplied by a negative gives us back a negative. So on the first interval, our expression will be entirely positive. Then we go to the second interval. Our test point is 5/4. So we plug 5/4 into the expression. So 2 times 5/4 minus 3 multiplied by 5/4 minus 1 squared. And recall, once again, we don't necessarily care what the value is, just whether it's positive or negative. So 2 times 5/4, that's going to be 10/4 or 5/2, and 5 halves minus 3 is negative. A square is always positive. A negative times a positive is negative. So our function is, and I made a mistake, in that first interval our function is negative. In the second interval our function is negative. And lastly, we need to check at this test point x equals 2. So if x equals 2, we have 2 times 2 minus 3 multiplied by 2 minus 1 squared. 4 minus 3 is positive. A square is positive. A positive times a positive is a positive. So we are positive in the third test interval. So at this point, we go back and we think about what the original question was asking. For this polynomial expression, where is it bigger than or equal to 0? Well, note in terms of our graph, it's equal to 0 at 1 and at 3 halves. And it is going to be bigger than 0 to the right of 3 halves. So in terms of our solution, we would say that we are bigger than 0 or equal to 0 at the number 1, or, so union here, at 3 halves and all the way to the right. So the sit containing just the single point 1, where the function is equal to 0, and then 3 halves all the way to infinity.